Everyone, Mr. Fritz here. We're going to talk about vectors in this video. Here's an introduction to vectors. Let's see what they're all about. Before we talk about what vectors are, or at least how to use them, let's actually think about what a vector is. And really the best way to think about vectors is to think about motion. So imagine this. Imagine an airplane is flying in a straight path, but airplanes usually don't fly without any sort of wind resistance or wind pushing against them. So kind of imagine what's going on in this animation. That plane wants to fly in one direction at a certain speed, but here's a whole bunch of wind pushing it in a direction other than the direction it's moving. So I'm going to stop this plane if I can, and there we go, and stop this wind. And let's think about what's going on here. The airplane is trying to travel at a certain speed in a certain direction, but we have this opposing wind that is moving against the flow in this completely opposite direction. And so because these two opposing forces or winds or directions are against each other, what's going to happen is basically the plane's motion is going to be the result of these two forces, the plane's thrust and the wind pushing against it. And really to compute these quantities and the direction and bearing of these things, we use vectors. That's what they're for. So if you can visualize what that is, that's going to really help you moving forward. Basically what a vector is a quantity that has both a size and a direction. So some examples would be like velocity, momentum, force. They all have sizes to them, but it really matters which direction they're moving. They can't be described without a direction. And then also we should consider what a scalar is. A scalar is kind of like a vector, except it just has only a size but no direction. So if I talk about the speed of something, if I say a car is moving 30 miles per hour, you know how fast it's going, but you have no idea which direction it's going. If I say the mass of an object is 50 kilograms, it doesn't give you any direction, just 50 kilograms is just a quantity. And volume is another example. So it's a quantity that is not moving in a specific direction, like a force might. If you're pushing at a certain force and in a certain direction, and that matters. So let's talk about how we represent vectors. There's lots of ways we can represent vectors. We can represent them graphically, we can represent them notationally, and here's how we might represent them graphically with these. We call them directed line segments. They're kind of scale diagrams where we show a line segment that has a size to it, and you can see that the angle also has, this has a size, and the angle or the bearing has a direction. So this segment or this line, this vector, would be a whole lot different if it were any bigger or smaller, or if it were rotated any differently. You can also look at it something like this. This is also kind of like a bearing representation where north is 0 degrees, and we would say this has a bearing of 45 degrees, this vector. And then typically when you see these directed line segment representations, you usually have some sort of scale to represent these vectors. What's nice about vectors is if you are very precise about the size that they are used, or the size to which they are drawn, you can gather a lot of information about them, or at least use the picture to authentically represent that quantity. So scale is important. Some of the other ways that you might see this vector is an arrow that is given a beginning point and an end point. We might name that vector by just a one-letter name. So there's lots of different ways we can call this vector, and I'll talk about that in a second. But how you would say whatever this thing is that's drawn right here is, you would say it by saying this vector emanates from O and terminates at A. So that's just kind of how you say it begins here and ends here. It emanates from O and terminates at A. Let's talk a little bit about the notation for a vector such as this one here. You might see it written as OA with an arrow over it. Notice that the arrow is ending at A. You could say it emanates from O and terminates at A. That's what this representation gives you. This is not the same thing as AO, and we'll talk about that later on. You could also see this vector represented with kind of a bold A, if we named this vector A. This works as well too. Or you might see it written as the letter A with a normal font and then a little underscore underneath it. So these are all notations for vectors. All of these represent vectors. So let's talk about what the magnitude representation might look like. Let's just talk about what the notation would be. This would be, again, kind of like a vector, except if it's just a magnitude, it is just a size or a length of that vector. So it doesn't require any sort of direction to it. So you might see it written as, like before we had OA with the arrow over it, but what denotes this as the magnitude is by putting these bars around the outside. Or you might just see OA by itself without the arrow. You can think of it as like encompassing the size but not the direction piece. That's why the arrow is gone. Or you could see it as, if we wanted to use that bold A, we could put that bold A in bars, or you could also list it with that A, with regular A with underscore, and put the magnitude bars around as well. So basically, this represents the size. And this is kind of like, if it looks familiar, this is kind of like absolute value. And the absolute value notation, if you recall, is what the size of a number is. The absolute value of -3, well, that's like the size of the value -3, which is equal to 3. And it's really used in the same way with these vectors and magnitude representations. So let's see how we can use these vectors. And we're going to draw a scale diagram in this example. And we're going to sketch a vector which represents a force of 20 newtons in a southerly direction. So here I have a little ruler on my screen, and basically this is going to help us to create a scale. We can make it whatever we want, and I want to make something that is 20 newtons long. So let's just say that I call 5 centimeters equal to, let's say, 10 newtons. So this is going to be my scale that I've created. So that means that if I want a 20 Newton line segment or size of a vector, I'm going to need 10 centimeters, since that means that 10 centimeters is going to equal 20 newtons. So that means that I can take a 10 centimeter line segment that'll go from here to here about. And so there's my 20 newtons, but I want this to be in a southerly direction. So what's kind of nice about this is I can take this vector and let's rotate it so that it's a southerly direction. And that's going to be a 20 Newton vector. So that has a size that's exactly this big, and it's pointing directly south. So there we go. That's the first example. In the second example, we want to draw a scaled arrow diagram representing 40 newtons on a bearing of 115 degrees. And this time let's use a scale. If we want 40 newtons, let's actually go a little bit smaller. Let's say that what did I say last time? I said that 5 centimeters is 2 newtons. Let's say that 2 centimeters is equal to 10 newtons. So that means that in my scaled arrow diagram, if I want 40 newtons, that's going to be it's going to be 4 times this amount, so 8 centimeters. So now I need an 8 centimeter length, and that's going to be from here to here about. So that takes care of the size. Now I need the right direction. So why don't we do this? To create a bearing of 115 degrees, what that means, a bearing by definition is the rotation in a clockwise direction away from true north. So this is going to be, north is going to be 0 degrees, due east would be 90 degrees, due south would be 180 degrees, and due west would be 270 degrees. Unfortunately, this is like completely different than what we've just spent a whole lot of time talking about with the unit circle, but that is the way bearings work. So if I want a bearing of 115 degrees, then that means I'm going to take this arrow and I'm going to bring it down to somewhere between 90 and 180, probably something like this. And let's label this as 115 degrees, and it has a size of 40 newtons. So this is kind of like what my drawing should look like. It has a size that's based on a specified scale, and it has a bearing or direction. That's what makes this a vector. So here's an example that you should try on your own now. Take a ruler or centimeters, or actually anything, as long as you use a proper scale. It doesn't have to be 1 centimeter. and create a vector that represents a displacement of 35 meters in this direction, 70 degrees. So go ahead and pause the video and see if you can't get this answer that I'll show you in just a second. So here's what my answer looks like. It is a 70-degree rotation from true north, which is 0 degrees, and that is a size of 35 meters. And really, as long as the line is 3.5 centimeters, then you have followed the scale given to you. Why don't you try another one, kind of like the same thing, using a scale of your choosing, using a scale of your choosing. Let's just use one of those. We want to sketch a vector to represent an airplane taking off at an angle of 8 degrees to the runway with a speed of 150 kilometers per hour. Give this one a shot and hit pause or play when you are ready to see the answer. All right, so this is what my diagram looks like. I am given an angle measure, but this is not a bearing. It is an angle of elevation from a runway. So this, if you drew something that looked like this and you called this here 8 degrees, that's not quite what this is asking for. The scale that I use here is 1 centimeter is 30 kilometers an hour, and this big line, this vector here, should be about 5 centimeters long. So that's just drawing these things. Let's talk a little bit more about some of their properties. Vector equality, this is on the back side of your notes, and by definition, two vectors are equal if they have the same magnitude and the same direction. So that should make sense, since what a vector is something with a magnitude and a direction. If they're equal, it should have the same things of those two quantities or characteristics. So when they're drawn, they are parallel and they're equal in length. So if I have some random vector that looks like this, let's call it AB, then an equal vector would be something that has the same size, it has the same direction, so in essence it is parallel. And actually I can make a copy of this quite easily and say that this is an equal vector. It's parallel, it's equal in length. Actually, I can move it anywhere I want, and it's still the same or equal vector. I can name it whatever I want. This doesn't have to be AB anymore. This could be vector JK, but it still is parallel, it is still equal in length, and so they are equal to each other. So what's nice and convenient that we'll see later down the road is that vector equality gives us the ability to translate vectors and move them all over the place. So there's going to be some strategy to moving these vectors when we add them, when we multiply them, when we subtract them. You'll see that later on down the road. Negative vectors, this should kind of make sense. Negative vectors are negative if they have the same magnitude, they have to be the same size, but they're the completely opposite direction. So when they are drawn, they are parallel, they have the same length, but complete opposite directions. So again, if I come up with some vector AB, a negative vector would be exactly the same, just about exactly the same. In fact, I am going to clone this and see, can I change the color of this? Ooh, yeah, that's nice. So this is going to be my negative vector. The only difference now is that the arrow is on the other end. And that should make sense. If it is an opposite vector, or if it's a negative vector, it should emanate and terminate from two different spaces. So we can call this vector CD. So we would say that vectors AB and CD are negative vectors of one another. You could also say that vector AB is equal to negative vector CD. And in general, you can make the statement that any vector AB is going to always equal the negative of its negative vector BA. So this is just a true statement all over the place. But again, these are parallel, they are the same size, they just terminate and emanate from different spaces. So why don't we take a look at these some examples of what this looks like when we combine all this stuff with vector equality and negative vectors. So here's an example where you have a parallelogram that's made up of a couple of vectors and a couple of parallel sides. And we want to find vector expressions for these four quantities. And we're given here that PQ, which is this vector right here, is also called A, and we are also naming QR to equal B. So if we wanted to find an expression for QP, that vector would be the vector created that is emanating from Q and terminating at P. and that is going to be the parallel and same size, same length vector as A, however it's in the opposite direction. So this is going to equal negative vector A. Let's see for letter B, RQ is the vector that emanates from R and terminates at Q, and it looks like it is kind of a lot like the last example. It's same size and parallel as vector B, but it's emanating from R and terminating at Q. So this is going to be negative vector B. Moving right along, for C we have SR, that vector, and that's going to start from here and end here, or I should say emanate from S, terminate at R, and that's going to be the same size, the same direction as vector A, and it is, because it's moving the same direction, it is parallel, and it's not terminating and emanating from opposite spaces. Everything is the same about this vector, it's just in another space. So this is going to equal the same vector as vector A. These are equal vectors. And then finally for SP, this vector, it's going to emanate from S and terminate at P. We can see that, actually let me do that in a different color. It's going to emanate from S and terminate at P. It is exactly parallel to vector B. It is the same size as vector B, however, it is in the opposite direction. So this is going to equal the negative of vector B. So there you go. Basically analyzing parallel vectors, same size, and just looking at the direction that they are pointing. So here's an example that I'd like you to try. Pause the video and read this question out, and from these given vectors, see what is equal, same direction, all this stuff right here. So give this problem a shot. All right, the answers here are listed below, so take a look at those, see if you got the same thing. We've got one more you try. Here's a little bit more complex of a diagram where you have these two triangles with all kinds of vectors all over the place. They're all named different things. And once again, I want you to evaluate these statements and tell me which of these statements are true. So pause the video, give this one a shot, and then come back when you're ready to see the answers. All right, here are the answers for this final you try problem. Hopefully it went okay, and really the whole sense of what we're getting after is what is a vector and what are equal vectors and negative vectors. So hopefully this video helped you with your introduction to this pretty big topic.